When the European Space Agency's Euclid telescope pointed its cameras at the Perseus galaxy cluster for the very first time, it was supposed to be a simple calibration exercise, a chance to show off what the newly launched telescope could actually do before its real scientific mission began. Instead, in the very first 24 hours of observation, Euclid captured something that immediately broke one of astronomy's most basic, long-standing assumptions about how stars behave once they are torn away from their home galaxies. Researchers expected those lost, wandering stars to drift toward the nearest large galaxy and settle into orbit around it, the same way a lost child in a crowded space instinctively gravitates toward the nearest adult. A comparison the research team themselves used to describe just how intuitive and ultimately incorrect that initial assumption turned out to be. That is not what Euclid found. What it revealed instead left the research team openly describing themselves as surprised, and what they discovered still has scientists working to explain exactly how something that should not have been possible, according to standard models, actually happened. To understand why this finding mattered so much, you first need to understand exactly what Euclid was built to find in the first place. Launched from Cape Canaveral in July of 2023, Euclid is a European Space Agency mission designed with one overwhelming goal in mind, mapping the invisible influence of dark matter and dark energy, the two mysterious forces believed to make up roughly 95% of everything that exists in the universe, despite the fact that nobody has ever directly detected either one. Rather than zooming in tightly on individual, spectacular objects the way some other space telescopes do, Euclid was built to observe enormous swaths of sky at extraordinary resolution, eventually charting the shapes and positions of literally billions of galaxies across roughly a third of the entire night sky over its planned 6-year mission. Before that main survey began in earnest, mission scientists released Euclid's very first images to the public in November of 2023, and then followed up in May of 2024 with a deeper, more detailed batch of what are known as early release observations, the first genuine scientific results to come out of the mission. It was within that early release data that a team led by University of Nottingham astronomer Nina Hatch made the discovery that would upend expectations. The researchers were studying something called intracluster light, an extraordinarily faint glow, found drifting in the empty space between galaxies within the Perseus cluster, one of the most massive structures in the observable universe, sitting roughly 240 million light-years from Earth. That glow, the team determined, comes from what astronomers call orphan stars, stars that have been violently ripped away from their original home galaxies through gravitational interactions with other galaxies, left drifting freely through intergalactic space with no galaxy left to call their own. Euclid's data revealed an almost incomprehensible number of these lost stars scattered throughout Perseus, an estimated 1.5 trillion orphan stars in total, producing a diffuse blue light so faint that it measures more than 100,000 times dimmer than the darkest night sky visible anywhere on Earth. And yet, once you add together the combined light from every single one of those trillion-plus stars, it accounts for roughly 20% of the entire cluster's total luminosity. Before we go any further into exactly what these trillion orphan stars did that nobody expected, if a genuinely impossible-seeming astronomical finding, one that scientists themselves openly admitted took them by surprise, is the kind of story that fascinates you, go ahead and hit like and subscribe right now so you catch the next one. Simply detecting that many orphan stars would already have been a remarkable achievement on its own, confirming Euclid's extraordinary sensitivity right out of the gate, well before mission scientists had even begun the telescope's main 6-year survey. But the real surprise came once Hatch and her colleagues started analyzing exactly how those trillion orphan stars were actually moving through the cluster. Standard astrophysical models make a fairly intuitive prediction about what should happen to stars ripped away from their home galaxies inside a massive cluster like Perseus. Once stripped free, these lost stars are expected to gradually fall under the gravitational influence of whichever galaxy happens to be most massive and closest to them, eventually settling into orbit around that dominant galaxy, the same basic physics that keeps planets orbiting stars and moons orbiting planets. Perseus has an obvious candidate for that role, its single brightest and most massive galaxy, a giant elliptical galaxy called NGC 1275, which sits at the very heart of the cluster and should have functioned as the clear gravitational anchor pulling every nearby orphan star into orbit around it, exactly the outcome standard theory would have predicted before Euclid actually looked. That is not what Euclid's data showed. Instead of orbiting NGC 1275 the way standard models predicted, the trillion-plus orphan stars in Perseus appeared to be orbiting him an entirely different point in space, a location sitting between NGC 1275 and the cluster's second brightest galaxy, NGC 1272, rather than centering cleanly on either individual galaxy at all. That result genuinely puzzled the research team, since nothing in conventional models of galaxy cluster formation predicted stars settling into orbit around an essentially empty point in space located between two separate galaxies rather than around one clearly dominant gravitational center. Team member Jesse Golden Marks, an astronomer at the University of Nottingham involved in the study, proposed an explanation that itself reveals something dramatic about Perseus's own violent history, suggesting that the misaligned orbits likely indicate the massive cluster recently underwent a significant merger with an entirely separate group of galaxies, an event energetic enough to have gravitationally disturbed either the Orphan stars themselves or the position of the dominant galaxy, ultimately producing the strange offset orbital pattern Euclid managed to capture. That merger explanation carries real scientific weight, because galaxy clusters like Perseus do not form instantly. They grow gradually, over billions of years, through repeated collisions and mergers between smaller groups of galaxies, gradually building up the enormous structures astronomers observe today, structures that can still carry the fingerprints of those ancient collisions long after the visible chaos of the merger itself has settled down. Finding direct, observable evidence of a relatively recent merger, preserved in the unexpected orbital pattern of over 1 trillion individual stars, gives researchers a genuinely valuable tool for reconstructing exactly how a cluster this massive assembled itself over cosmic time, using the displaced Orphan stars almost like forensic evidence left behind at the scene of an enormous, extremely slow-motion collision between entire groups of galaxies. There is also a deeper scientific reason why researchers care so much about tracking exactly where Orphan stars end up orbiting within a cluster, one that connects directly back to Euclid's core mission of mapping dark matter. Because these lost stars respond purely to gravity once they are stripped from their home galaxies, their movements effectively trace out the underlying gravitational landscape of the cluster, including the invisible mass contributed by dark matter that cannot be observed directly through any telescope. Nina Hatch herself emphasized this connection directly, noting that this faint intercluster light can help researchers map dark matter provided they can first work out exactly where the Orphan stars producing it originally came from. That is precisely why the misaligned orbital pattern Euclid detected matters so much scientifically, beyond simply being an unexpected curiosity. If Orphan stars are orbiting a point between two galaxies rather than around the cluster's single most massive galaxy, that pattern implies the underlying distribution of dark matter within Perseus is itself more complex and possibly more disturbed by a recent merger than existing models had assumed, directly feeding into the exact kind of dark matter mapping Euclid was built from the ground up to accomplish. The discovery also fits into a broader ongoing story about just how differently the universe often behaves once observed the actual careful math, rather than through simplified, intuitive assumptions. The lost child in a mall analogy Hatch and her colleagues initially expected Orphan stars to follow, drifting toward whichever galaxy happened to be nearest and most massive, works reasonably well as a simplified mental model, but Perseus revealed that real galaxy clusters carry a violent, complicated history written into the fine details of how their stars actually move. Untangling that history requires exactly the kind of precise, wide-field observation Euclid was specifically engineered to provide, distinguishing this discovery from a simple technological upgrade and positioning it instead as a genuine leap forward in astronomers' ability to reconstruct how massive cosmic structures actually assembled themselves over billions of years of gravitational interactions, mergers, and collisions between galaxies and entire groups of galaxies. Now, the Orphan star mystery was far from the only surprise buried inside Euclid's first images. Using the same early release data, Hatch's team also identified more than 50,000 individual globular clusters, tightly packed spherical collections of anywhere from tens of thousands to millions of stars, scattered throughout the Perseus cluster. Analyzing the chemical composition of stars within those globular clusters revealed something else worth noting, a distinct lack of heavier elements, what astronomers call metals, pattern that suggests these clusters originally formed far out at the periphery of the larger galaxy cluster before gradually migrating inward over time, adding yet another layer of evidence supporting the picture of a massive, still actively evolving cosmic structure, rather than the calm, settled system many earlier observations had assumed Perseus to be. Even beyond Perseus, Euclid's very first batch of released observations delivered a genuinely wide-ranging set of discoveries that collectively demonstrated just how much this telescope was capable of finding, almost immediately, before its main survey mission had even properly begun, a pace of discovery that surprised even some of the researchers directly involved in analyzing the earliest data. Researchers studying a different early release field identified free-floating, or rogue, planets hidden within a dense stellar nursery in the Orion constellation. Planets not gravitationally bound to any star at all, drifting alone through interstellar space. In a separate portion of the same dataset, scientists discovered an entirely new dwarf galaxy sitting quietly beside NGC 6744, a well. Studied, extensively observed nearby spiral galaxy that astronomers had already examined countless times using other telescopes, yet somehow nobody had previously identified the small companion galaxy hiding practically right beside it, invisible until Euclid's exceptional sensitivity finally revealed it. That pattern, genuinely significant discoveries emerging almost immediately from what was technically meant to be a preliminary, calibration-focused batch of images, says something important about what the rest of Euclid's 6-year mission is likely to produce. ESA's own Euclid project scientist, René Lorais, described the Orphan star findings and the broader early release results as offering only indirect detection of dark matter so far. A careful, scientifically honest acknowledgement that these results, while genuinely exciting, represent just the very first steps toward the mission's ultimate goal, rather than a final, complete answer about the true nature of the universe's missing mass. That kind of careful framing matters, because it distinguishes between two very different kinds of surprising results: findings that overturn basic physics entirely, which this was not, and findings that reveal our existing models were incomplete or oversimplified, forcing scientists to refine and improve their understanding rather than throw it out altogether, which is precisely what happened here. A distinction that matters enormously for how the broader public should interpret a headline this dramatic. If watching a telescope overturn basic astronomical assumptions in its very first batch of images is the kind of story that keeps you coming back, make sure you are subscribed and have hit like on this video, because there are far more genuinely surprising discoveries like this one still waiting inside the data Euclid has yet to fully analyze. What makes the Perseus Orphan star discovery particularly compelling, beyond the specific scientific puzzle it presents, is what it reveals about the value of simply pointing an extraordinarily sensitive new instrument at a well-studied target and carefully looking at what nobody previously had the ability to properly see. Perseus is not some obscure, previously unexamined patch of sky. It ranks among the most extensively studied galaxy clusters in the entire history of modern astronomy, observed repeatedly using X-ray, telescopes, radio telescopes, and every major optical observatory built over the past several decades. Yet it took Euclid's specific combination of wide field coverage and extraordinary sensitivity to finally reveal that faint, ghostly population of over 1 trillion orphan stars, and it took carefully analyzing exactly how those stars were moving to discover that even a cluster this thoroughly studied still had genuine, previously undetected structural secrets left to reveal. That is, in many ways, the entire promise of Euclid's mission distilled into a single early result. This is a telescope explicitly designed to observe enormous volumes of the universe with a level of precision no previous survey instrument has ever matched. And if its very first, technically preliminary batch of calibration images already managed to overturn assumptions about how orphan stars behave inside one of astronomy's most well-known galaxy clusters, it raises a genuinely exciting question about what else remains hidden inside the billions of galaxies Euclid still has left to survey over the remainder of its 6-year mission, waiting for exactly the kind of careful, patient analysis that turned a routine calibration image into a genuine scientific surprise. Perseus, a cluster astronomers have pointed telescopes at for generations, still had a trillion-star secret waiting to be found, hiding not in some faint, unexplored corner of the image, but in the simple question of exactly which direction those stars were quietly drifting.